continue talking about speech and speaker recognition. We'll call it part 2, even though it's probably part 3 or 4. What I want to talk about today is sort of the second major way, or third, I guess, major way to look at speech and speaker recognition. If you recall, the first, sort of historically, the first thing people did was to look at a frequency spectrum, look at things like frequency spectrograms and things like that, and then people moved on to the cepstral models. And so what I want to talk about today is sort of what came next historically and is still used to some degree today, prior to the just massive influx of neural network models, and that is the hidden Markov model. So we will discuss Markov and hidden Markov models, and then use that to lead into the next sort of historical development, which was more of a machine learning and AI approach. So Markov and hidden Markov models, abbreviated HMMs, are methods that find and define patterns over space and time. They're statistically based methods. They're applicable to speech recognition because they can take into account both the timing variability between speakers. And they were one of the more recent techniques prior, as I said, to the dominance of machine learning and neural networks in speech recognition. Some other motivations for using hidden Markov models include the fact that a lot of real-world processes are sequential, so the process will unfold over time, which of course, as you know, means you have a non-stationary process and makes it difficult to model with Fourier analysis. And the event producing the output is often hidden. Also, internal states of a system, for example, the internal states of a voice producing speech, are often also hidden. So we actually don't, for individual people, make these elaborate physical models of the voice box and the vocal tract. It was always difficult. It's actually less difficult now to model that physics because we have so many multi-physics type solvers, but it's still an incredibly computationally expensive process, and it's just not really a way we approach things, because for every different speaker, a word would have a completely different physical model. So it's good to have a methodology where you can have the internal states of the system that are hidden. An example of where hidden Markov models are still used and Markov chains is I'm working on a project right now where we're looking at action potential firing of neurons. And so that's a classic case of where you can observe the effects that something has happened, but you can't actually observe the internal state of a neuron. So a hidden Markov model is sometimes appropriate for that kind of thing. So let's look at this automated speech recognition using hidden Markov models. So first, let's talk about what a hidden Markov model is not. It does not model a deterministic pattern. So a deterministic pattern, so this is just a silly example of traffic lights and traffic lights in the UK, where you go from having a red light to a red and amber light to a green light, back to an amber light, and then to a red light. And it's the same pattern every time. Here in the States, you can put a little bit of logic in it. For example, if you activate a left turn signal, you might at some point in this process get a left arrow. But once again, it is always deterministic. We know that a left turn signal is activated if a person, drives over the strip that activates the left turn signal. So there is a known process of events that occurs. It's not statistical, hopefully. Hopefully there is not a statistical noise-based process that randomly turns lights from red to green to yellow with certain probabilities, because even if the probability was very, very low, the results would be catastrophic should it happen. So deterministic pattern is not modeled by the hidden Markov model. So Markov models are non-deterministic. They don't always follow the same sequence of states, and each state transition is determined by previous states that give what we refer to as an nth order Markov process. So each state transition is determined by the previous state. We're mostly interested in this case in speech recognition in first order models. And so shown here in the figure is an example of a first order Markov process. So what you see here is you see a Markov model of weather. And so the three possible states on any given day are sunny, cloudy, or rainy. And what the arrows represent is sort of the movement from one state to another. So, for example, in this figure, you could start off on a sunny day, and the next day it could still be sunny, so you would have this loop. Or the next day could be cloudy, so you would go from sunny to cloudy without rain. Or the next day could be rainy, so you could go from sunny to rainy. And this might not be the best logical model, because one could argue that you would have to become cloudy before you could become rainy. But let's pretend that it works like this. And so this is an example of a non-deterministic pattern and a first order Markov process, and the weather has what we call three states. And so what you have to have is you have to have like an initial state probability vector pi. So what that will tell you is this is the probability that we started sunny. And then you have to have what the states are, and you have to have the initial states, and then you have to have what is the probability of each of these transitions. So you'll see in people who do Markov work, these arrows here will often be weighted, so they'll have a number next to them. And so if you start off sunny, you have three possible directions you could go. Those three should all add up to 1, because that's the probability that it will be either sunny or cloudy or rainy the following day. So you have your initial state, and so that is referred to as the state transition probability matrix A. So we'll show another figure in a minute that kind of illustrates a little better what these probability matrices look like. But this is just the diagram of a Markov process. So here's the probability. So the probability of a sequence of states. So what we want to know is, what's the probability that it's sunny on day 1 and it's cloudy on day 2? And we might even want to know even more than that. We might want to know sunny and then cloudy and then rainy on day 3 and then rainy on day 4. So what the transition matrix is it's just a set of probabilities that allow us to go from the weather today to the weather tomorrow. So for example, if it's sunny today, there is a 0.5 or 50% probability that it will be sunny tomorrow in this model, a 25% probability that it will be cloudy, and a 25% probability that it will be rainy. So these are assumed to be independent states, but the probability of going from one state to the next is given in this transition matrix A. And so you can see that in every case in this model, you're more likely to stay in the state you're currently in than to transition to another state. So one of the biggest challenges in the Markov model is to figure out, first of all, how you get these transition probabilities. Is this empirical data based on a large data set that would assign these probabilities, or is there some physical reason behind this, or some historical reason? So assigning the state transition matrix A values, it's assumed that that these somehow come from some a priori knowledge of sort of the probabilities. So Markov models aren't always appropriate for systems where the state of the system is not observable. For example, the neurons in your brain. We cannot, on an individual neuron basis, measure what's going on with each neuron voltage, because you have millions of them in even one tiny part of your brain. So what we have to measure is some observable something that lets us know that is connected somehow to these hidden states. In this case, we're going to assume the weatherman is locked in a closet with no video access and can't figure out what the actual weather is outside. So he or she would need something to observe to be able to tell, to connect to the weather. So in this example, a barometer is used. So what you're actually observing is you're observing the barometric pressure, because I guess you can be electronically connected to a barometer. In speech, once again, we don't know, we're not measuring the vocal cord activation, we're not measuring what the tongue is doing or any of that in the speaker. So all we really have to observe are acoustic features. And so we hope that then helps us determine these hidden vocal states. So these are the types of problems that hidden Markov models are designed to solve. So for a hidden Markov model, each state is not actually observed, it's hidden, and only a set of observations of the system are available, and that would be the outputs. So it's almost like you're trying to solve backwards. Given a set of outputs, how do you connect those to what the state was? So a hidden Markov model is comprised of two sets of states, the hidden states, which are the true states, and they can be described by a Markov process, similar to our little weather example. And the observable states, which are the visible states like barometer readings, etc., formants in speech. A particular hidden Markov model is defined by three parameters, pi, a, and b. So pi is the vector of the initial state probabilities. So today, what is the probability, given the barometric pressure, that it is sunny, cloudy, or rainy? A is the state transition matrix, meaning based on today, what will tomorrow's state be, assuming a first-order Markov process. B is the emission probability matrix, and this is a matrix that gives the probability of each state occurring at the same time as an observation. A and B are assumed to be time independent, but the fact is this is unrealistic in practice. So B ties the state to an observation. So for example, if you read a certain barometric pressure, there may be some atmospheric science that tells you that given this barometric pressure, there is an 80% chance that it is clear outside. A 10% chance that it is cloudy, and a 10% chance that it is rainy. And while a different barometric pressure reading might be an 80% chance that it's cloudy, a 15% chance that it's rainy, and a 5% chance that it's clear. So that's what the B matrix gives you a feeling for. So the way hidden Markov models are represented schematically is you have these hidden states, in this case blue, green, and yellow, and then for each state you have an observed variable. So this would not mean, for example, that we had 3 different barometers for each day. It would mean we had a knowledge of the range of the barometric pressure for rain, for clouds, and for sun. So these are not necessarily 3 separate sensors. They're 3 separate conditions observing the hidden states. So in this first order hidden Markov model, Q sub t is the state at time t, and Y sub kt is the observed state at time t. And K is the index of the observed state at time t. So initially we have this initial observation at time t. At time t plus 1, we have the next observation, which would be Y, and some change of state, and then we have another change of state distribution or not, and then the third observation at Y k plus 2. So barometer reading on day 1, day 2, and day 3 respectively. Weather on day 1, day 2, and day 3, which is not observable. So lambda is this triple of parameters that define the hidden Markov model. We talked about this is just a mathematical representation. So the vector of initial state probabilities, lowercase pi sub I, is just the probability that your initial state is in state I. And Aij is the probability of the state transition, meaning you're going from state S sub I to state S sub j at measurement point t plus 1. And B is the emission probability matrix, meaning that you're looking at the probability that Y is some Q sub at Q sub t, for Q sub t, is equal to this jth state. So in other words, the probability that you transitioned from the output, from the original output, or the probability that your observation picked up on the state that you were in. M is the number of observation states, and the observed time state at time t is y sub k, where k ranges from 1 to m. And T is N is the number of hidden states, and they're denoted by S, ranging from 1 to N. M and N do not have to be equal. The hidden state at time T is Q sub T, which is a member of S. So here is an example of what these matrices look like. So we're going to illustrate a 3 hidden state Markov model example. The example is pretty much an extension of what we saw. We still have our sunny, rainy, and cloudy. And today we're going to say there's a 50% chance that it's sunny, a 20% chance that it's cloudy, and a 30% chance that it's rainy. For tomorrow, we need to look at this state transition matrix, which says if it's sunny today, there's a 0.5 or 50% chance it will be sunny tomorrow, a 25% chance it will be cloudy, and a 25% chance it will be rainy. And then finally, we look at the emission probability matrix. So under observation here, we have high, medium, and low barometric pressure. So for high barometric pressure, today there's a 70% chance that it's sunny, 30% that it's cloudy, and 30% that it's rainy. But these are less like, these are not viewed in quite the same way, because you notice they don't add to 1. What adds to 1 is the rows. So it's more like, the better way to say it is to say, on a sunny day, there's a high probability that the barometric pressure, there's a 70% probability we'll read a high barometric pressure, a 20% probability it will be medium, and a 1% probability it will be low. So this just tells us how good is our observation. Now this one, it's pretty easy intuitively to see that you could collect some experimental data that ties your measurement or observation to the state. So even in speech, if we could identify formants and then, look at, in an observation, look at the formants, if we had some identification with what sound that was associated with, then that would fill this matrix. So let's say we had sounds A, E, and ah, and we were looking at formant ranges in, say, a Kepstrel or even a spectrogram. It's easier to view on the Kepstrel coefficient. So if we were looking, at something like that, take enough data on A's, E's, and ahs or uhs, and you would get a feeling for where your formants lie. And so you could assign a probability that 70% of the time, if we observe a formant in this frequency range that is associated with the sound A, 20% the sound A would lie maybe at a slightly different range, and 10% that it would be even more different. So that's kind of physically where these come from. So you can see how this would be not impossible to collect empirical data. The state transition matrix, a little more difficult to make predictive data of based on the current state, what comes next. but I think, you can sort of make the leap that if you have a certain sound, there are higher probabilities that it is followed by a similar sound. So let's think about the word I just said, followed. If it starts with F and then goes with O, I'm thinking of FO words. Fortune would be different, follow would be different. And so it would be the kind of thing like, what's the probability that it's a fall sound, FOL, as opposed to FOT? So it would be that kind of thing that you would be trying to predict. So this one, to me, intuitively is more difficult. So there are 3 problems that are associated with hidden Markov models, and problems doesn't mean disadvantages, it just means 3 problems to solve. The first is the evaluation. That is calculating the probability of an observed sequence of observations given a hidden Markov model. So when we have a lot of hidden Markov models, we need to evaluate which model is most likely to have generated, in terms of probability, a set of observations. So we could, for example, train the model to be a summer model and a winter model and find probabilities with each model, the probabilities that the observations have been generated by the model. So in weather, that might make sense. Particularly, it might make sense in West Texas. I think about dust, and they're able to predict dust pretty accurately. And a lot of it is based on the barometric pressure and the relative humidity. So either one of those might have a model in the spring as compared to a model in the winter and compared to a model in the summer. They all might be quite different. So you can have different HMM models for different circumstances. Decoding is about finding the most probable sequence of hidden states given a set of observations. So, in other words, given that you make observations over, a 3-day period, what's going to be the most probable sequence of what will happen on day 3? So, in other words, sunny, 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 cloudy, rainy, sunny, rainy, cloudy. Which of those would have the highest probability? And then generate the parameters of a hidden Markov model from a sequence of training observations. So there is usually some machine learning, especially in today's world, associated with hidden Markov models. So this is mainly talking about sort of first order with 3 states and 3 observable states. And so what we want to kind of figure out is what's the probability of the observation sequence, where we could calculate going from a day where you had a high barometric pressure to a high barometric pressure on the following day and a low barometric pressure on the 3rd day. So if you look here, there are 3 hidden states and 3 days, and so you would have 27 possible different weather sequences. So the probability that you would have high, high, low observed in this particular system would be the sum of the probabilities of each possible association. So you would take the probability of high, high, low with sunny, 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 and add the probability of high, high, low with sunny, sunny, cloudy. And so you would then be doing what's referred to as kind of an exhaustive set of all the probabilities. And then that would give you an idea of the sequence for a given, the most probable sequence. Now that's very computationally expensive process because any exhaustive process is very computationally expensive. So it can be reduced by using recursive relationships, and in this particular case, this is the forward algorithm. Partial probabilities are denoted by a subscript I of j. That represents the probability of getting to a particular state. A subscript t of j. That represents the probability of getting to a particular state j at time t. So partial probabilities can be calculated, and we're not going to go into a lot of the statistical analyses here because it turns out that this is relatively easy to calculate on MATLAB. But given the information in your model, you're able to use this forward algorithm to make predictions. And so here's the expression for creating each partial probability. So what happens at time plus 1? Which J state do you go to? You can calculate that from the partial probabilities at time t. And it'll be the sum of the products of the relevant state transition matrix elements with the previous probabilities multiplied by the relevant element of the observation matrix. So what does that mean? That means you take your observation matrix and you multiply that by all the possible transitions to get to the next state. So this is just an example of the forward algorithm method to kind of go from the previous state to the current state. You're looking at all the possibilities. Then once you're in the current state, you're following sort of this trajectory that's most likely, and you're getting to a final state prediction. So it's not exhaustive. You're not having every state connected to every other state in this second step. And you're basing that in part by these observations. So the forward algorithm allows you to calculate an overall probability. After however many time steps, you can get a final probability, and that's shown here in equation 10.5. So that'll tell you, you're going to sum the final partial probabilities at time little t equals big T, the last time step, and get a probability of an observed sequence. Once again, that's calculated in the model because the key is having this B matrix. So in other words, how are your observations connected to your states, as well as your initial state, your pi's. So once again, the key here is knowing where you start, what is your initial state, what is the probability of from that state. So in the word follow, you have an F. If you're looking at formants, you have an F. And then you need to know what's the probability that the next sound is a ah instead of an A, like fake, or an E, like feed. You need to know that probability, and then from that probability, you need to know, given the fa, what's the probability of an L, like fall. And so you can kind of see how this evolves. So as an example, there are a couple of figures that show this forward algorithm using a 3 hidden state hidden Markov model. The hidden Markov model has 3 states that correspond to 3 phones and 3 observation states. And the observation state will be the first formants. The first formant frequencies f sub t quantized into 3 possible states, low, medium, and high. 3 time steps are shown in the bottom of the figure and are associated with a given observation sequence that's high, high, and low. The partial probabilities are calculated for the first 2 steps, and those calculations lead to the values located by the question marks to the right of the question marks. So let's look here at the figure instead of continuing to say stuff. Okay, so here is our vector of initial state probabilities. Here is our state transition matrix for different phones. This is A, E, and Ah. Or is that I think it's And then here's our observation, whether it's high, medium, and low, and kind of what the probability is. If it's an A, it looks like there's a high probability that's high. If it's an E, the higher probability is that it's medium, and the same for So if we look at partial probabilities, if we have an observation that is high, high, and low, then for A, we take the sum of these probabilities, and we end up getting sort of the distribution of that. The total probability then is the sum of all 3. So this is just, one example of how the hidden Markov model works. This is called a Viterbi algorithm because it is recursive. It is slightly less computationally expensive than both the computational and the slightly modified computational, the forward algorithm. But the Viterbi algorithm gives you kind of the overall total probability of going from state A to state B. So once again, partial probabilities represent the probability of getting to a particular state J at time t. It is the maximum probability of all the sequences that end at state I in time t, and the best path is the sequence of hidden states which leads to this maximum. So that gives you an idea, even though you don't know the states, as long as you know the number of states and the probability of being in that state on day one and of transitioning to that state at time t, then you can calculate a partial probability for each path. The Viterbi algorithm is recursive. There you would find the partial probabilities for each state at t equals 1, and then find the partial probability at t from the previous probability at t minus 1. So it's got a backward step. You're backtracking. So you could recurse the partial best paths from t equals 1 to t equals t, which is the end, and find the best by backtracking from the state at t to the state at 1. So it's just a difference in the algorithm approach. So hidden Markov models also involve learning. So by evaluating and decoding the problems, both these steps assume that the hidden Markov model is already defined. In other words, that pi, a, and b are known. So in speech recognition, there's usually a single hidden Markov model that is trained to represent a phone, an n-gram, a word, or combination of words. In order to train each hidden Markov model, multiple examples of the speech element to be recognized are required. So the parameters of the hidden Markov model are usually not directly measurable, so there has to be a learning mechanism, and so that's the learning problem. The forward and backward algorithm basically makes an initial guess at the parameters, and they're iteratively updated until a termination condition that gives the final approximation is found. The next guess for each iteration is usually based on the method of gradient descent derived from some error method similar to this expectation maximization. So if you have not had any pattern recognition, gradient descent is one of the classic and perhaps most straightforward methods where you're basically looking at error functions and you're minimizing the error functions by trying to find an absolute minimum. So MATLAB has hidden Markov models built in, and I'm pretty sure this is in the statistical package. The code that follows on the next page will show you some hidden Markov model commands. These three commands, GMM generate, code, and Viterbi, use the definition of a state transition matrix A and emission probability matrix B. The initial state of the sequence is assumed to be in hidden state 1, so you actually don't need an initial state probability vector. Generate generates an observation sequence. Decode generates the partial probabilities of each hidden state at each time step. And hidden Markov model Viterbi generates the most likely hidden state sequence. So here's the output. So you have your states, you have your sequence. It generates that. So you give it your A matrix and your B matrix. It generates a sequence. It generates states, and then your decode will generate your different routes from beginning to end, and your answer comes out when you give it the Viterbi command. You can also train your hidden Markov model using HMM estimate and HMM train. So quite a bit of resources available within MATLAB for constructing hidden Markov models. So hidden Markov models for speech. So far we've talked about general use. Speech recognition is, indicated here in figure 1012. These are temporal type hidden Markov models. You're typically looking from left to right, so there is a sequence constraint, and that makes sense because we don't just have randomly occurring sounds. We have sequence sounds. So there is a sequence constraint. The progression of states can only be sequential or self-loop. So in other words, you cannot go forward and then come back. It's all forward. A hierarchy of these types of models can be used to handle different speech timing, pronunciation, grammar, and hidden states all within the structure. So the hidden states are actual phones, and then the A11, A12, etc. are the A matrix state transitions. So you can see that there is not an A32, that would be 0 because that's not allowed, nor is there an A31 or an A21. So some of the transitions are missing because we're assuming we're going only forward in the model. So the hidden Markov model emission probability estimation. So in the above examples, the observation states are discrete, but observations are often continuous, and so you have to figure out how you're going to model continuous readings. So one thing in discrete probabilities is to use vector quantization. In order to derive observation states, the input feature vectors are quantized into bins. So for example, for barometric pressure, your high would be pressures over 110, your medium would be pressures 90 to 110, and your low would be pressures under 90. Gaussian densities are parametrically controlled density functions defined by mean and covariance, and Gaussian mixtures would be a weighted combination of Gaussians, and then finally neural networks. So that's how we're sort of estimating things. This is just a figure that sort of shows how this would work schematically. So you have some input audio, and then from the input audio you do some feature extraction. The male frequency Kepschel coefficients would be one possibility. And then you look at your observation sequence. So you've basically got this sequence, and you're looking at that, and you've got your hidden Markov model for word 1, for word 2, for word 3, and so on. You then take the probability outputs, and you see which one is the maximum. And then based on that, which gives you the highest probability of sequence, which hidden Markov model, based on that, you would match the word to that hidden Markov model. So that's kind of interesting, I think. So in summary, okay, the hidden Markov model is pretty well defined in its mathematical basis and structure. You do not accumulate errors in the model, so you're not propagating and accumulating errors, and that's because you have an observation at each temporal step. It does not require the prior temporal segmentation of the signal. The temporal property of speech is accounted for, and it's used with features like the MFCCs or the MFCC delta or delta delta, or other invariant features that do not change a great deal from speaker to speaker. For individual word recognition, you can form a hidden Markov model for each word, and then you can use a maximum likelihood method to choose the found word. It can be combined with a lexical or grammatical model to perform continuous speech recognition, And finally, it can be combined with a Gaussian Markov model or a deep neural network emission probability estimation. So you can see that even though the Kepstrel coefficient and the hidden Markov model are older models, they're still often used to combine with more modern models like neural networks to kind of use the as a way to define the feature space. So if you look at Gaussian mixture models basically combine with hidden Markov models, and this was the dominant approach prior to deep neural networks, because the Gaussian mixture models allow you to be flexible in modeling these emission probabilities of continuous Kepstrel coefficient features from input audio. So you have this Gaussian mixture model that gives you basically a weighted sum of Gaussian probability density functions. So you have these density functions, you get a weighted sum, and that gives you your Gaussian mixture model. So if we look, okay, here's our speech recognition. So we have, these different sounds, and they're measured by this A11 would be, sort of probability. We're looking at most likely formants. Each of these formants has this, so you see how we have these Gaussians. So what this is, okay, if we look just at GMM1, so here's our word. So we got this word, and it's got 1, 2, 3 easily observable formants. So among those observable formants, there's a probability. So let's take the word, what's a good word with 3 sounds? Fox. Okay, so I have an F, an O, and an X. So fox. So there is for that first sound, that F, there's a probability that that's an F based on the formant. And we assume it has a normal or Gaussian distribution. For the aw in fox, there's also a probability distribution function that's an aw sound. It might not be. It might not identify it as the correct sound or the correct phone. And then for X, I guess, there's also a probability distribution of identifying that as that particular sound. Put it all together and incorporate the fact that you have some delays, you would see this Gaussian mixture model as the mixture of the probability that it was an F, an O, an F, an O, and an X. So you get this distribution function, or this Gaussian mixture model. So each word in this expression has its own Gaussian mixture model. And so by applying the Gaussian mixture model, you can get a better indication of the probability that your observation puts together 4 or K unique words. So I think that's pretty cool to combine this hidden Markov method with a Gaussian mixture model in identifying speech patterns. And as I said, this was widely used prior to the recent explosion of neural network technologies. So in the next lecture, we will discuss the application of neural networks to modern speech recognition, the move. So currently, the technology in recent years has been to combine this hidden Markov model with neural networks and use hidden Markov model as well as even Kepstrel coefficients as features. They are now moving toward an HMM independent neural network method. And so that is all of the publications at the International Conference on Applied Speech and Signal Processing. They're no longer signal processing, they are AI and neural network models. So we'll look at some of the modern publications, but first, in the next lecture, we'll discuss what the neural network models are.